Welcome to AP Chemistry at Hananiga High School. I'm Brian Brown, and today we'll be getting into our second set of notes from Chapter 13, dealing with factors that affect solubility, concentrations, and making of solutions. Chemists use the axiom like dissolves like, which we talked about in our last set of notes. And remember, that would mean polar substances tend to dissolve in polar substances. Nonpolar substances tend to dissolve in nonpolar substances. That's our fundamental axiom of solubility. Well, why does that work? Well, the more similar the intermolecular force attractions, the more likely the one substance is to be soluble in the other. And it really deals with our three energies. When we're looking at a situation where we have two polar substances, our solute to solute and our solvent to solvent energies are going to involve those types of things, breaking apart molecules that are polar and potentially hydrogen bond to each other, or just simple dipole-dipole attraction. So in a polar molecule situation, when we look at our third energy, the bonds that get formed when the hydration occurs, and remember, we're making quite a few of those bonds when we hydrate our molecules. Those are also going to involve that stronger type of attraction, which means we're going to get back a lot of energy. So really what happens is number 3 typically is comparable to 1 and 2 in those situations. And when we have nonpolar with nonpolar, the same thing ends up happening. Now, take a look at this case. We have the glucose molecule, which has OHs all over it. It's very soluble in water, and that's because it has all these OHs. It hydrogen bonds well with the water molecules. But if you put cyclohexane as your solvent and try and interact it, remember cyclohexane is a hydrocarbon. It's a nonpolar substance with only weaker London forces. The type of attraction we get from the glucose molecules, which are polar, to that nonpolar substances are very, very, very weak. And energy 2 and 1 are not going to be comparable to energy 3 because at least one of those two energies are going to involve polar breaking, and that's going to be a much higher energy than the small amount of energy we get back in the nonpolar dipole situation. So what would happen to the solubility of glucose if we got rid of those OHs and replaced them with methyl groups? Well, now we're going to have a bunch of C's and H's for the most part, and we would expect it to get significantly lower in solubility. And that's because we're adding a bunch of nonpolar parts, more hydrocarbons, to our molecule, and we're going to lose all those OHs, which would cause hydrogen bonding to water molecules. So we'd expect it to decrease significantly. Now, this actually plays a little bit of a role in some body chemistry situations. There are certain types of chemicals that are necessary to our body in certain quantities. They're vitamins. So vitamin A is a soluble substance in nonpolar compounds like fats. Well, if you look at the molecular formula for this vitamin, vitamin A, it has a huge nonpolar part and this tiny little OH on the end. So that'll hydrogen bond a little bit to water, but the vast majority of this molecule is going to be nonpolar. So this would be much more attracted to nonpolar things like the fats in your body, which are nonpolar. So vitamin A is fat soluble. It's going to get stored within our fats inside our body and not get carried by the bloodstream and filtered out by the kidneys. Well, vitamin C, on the other hand, tends to be soluble in water. And if you look at the molecular formula UCY, like glucose, it's got OHs all over it that help it hydrogen bond to water. So vitamin C is going to have a significantly higher solubility because it's much more like the water molecules. And therefore, if you take and ingest too much vitamin C, it just gets filtered out of the bloodstream by your kidneys and it really turns your urine funky colors more than anything else. But it's not going to create, by and large, significant health risks like megadosing fat soluble nonpolar vitamins inside your body because they can build in the fats because your body's going to be efficient. It's going to store them. And if you're not using them up, it's going to slowly build in concentration until it can potentially pose serious health risks. Now, the next thing we're going to get into is how pressure above the liquid can affect solubility. So the solubility of liquids and solids really does not change appreciably with changes in pressure above the liquid. So their solubilities are going to stay constant at different pressures above. But pressures of a gas above the liquid can play a huge role in solubility. So the solubility of a gas in a liquid is actually directly proportional to its pressure. Last time we talked about things that were directly proportional was back in our gas law chapters. And remember, we ended up with these equations from that. So we're going to come back to that when we get into what's called Henry's Law. But to finish up this idea, if you look at a nonpolar thing, so these are different hydrocarbons, methane, ethane, propane, and in general, these nonpolar substances are not going to be very soluble in a polar substance like water. But you will notice that the solubility, while it's not great, is going to slowly increase when the mass increases. Now, you have to be careful. It has absolutely nothing really to do with the mass. What it has to do with the fact that when our mass is increasing, we're increasing the number of protons, neutrons, and most importantly, we're increasing the number of electrons. So we're back to a Limpex situation here. So methane would be least attracted to water because it's going to be the most polar with the least dipoles that get induced within it through London forces. But the larger, more polarizable our electron cloud is, the stronger our attractions are going to be. And these larger molecules are going to have slightly stronger attractions to the polar water molecules. So while these are all nonpolar substances and not very soluble in water, it goes back to the concept of Limpec again. As we look at these substances' solubility, we would see it increase as the substance is getting bigger because of the larger, more polarizable electron cloud that is the result. Now, I mentioned that direct proportionality is something we'd come back to, and it's called Henry's Law. Henry's Law basically is the solubility of a gas equals K, which is the Henry's Law constant, times the pressure of that gas above the liquid. Increase the pressure above the liquid, you increase the solubility of the gas. So we can use this to keep something like CO2 dissolved in pop. CO2 is a smaller nonpolar molecule. It's not going to be very soluble in a polar substance like water. But if we increase the pressure above of the CO2, we can force more and more and more CO2 into solution through Henry's Law. Now, in this particular situation, unlike in the gas laws where the K was completely dependent upon the number of moles and the temperature, and therefore we typically got rid of the K if we were looking at the pressure volume situation, or get rid of the P if we were looking at volume temperature in Charles' law, we didn't use this form of the equation. Henry's law we sometimes do. So you should be able to use Henry's law in this case, as well as if we solve for K and look at changes, we can look at it in this form, like any of our other direct proportionalities, Charles and Gay-Lussac's and Avogadro's laws that we looked at back in the gas law chapter. They always look like this. That's because this is how that K is going to solve. So this is the other form we sometimes use Henry's law in. So if we know the solubility at a given pressure and we increase the pressure above, we can calculate the new solubility of the gas in the liquid. And you should be able to solve Henry's law problems from this type of situation as well. So calculate the concentration of CO2 in a soft drink that is bottled with a partial pressure of CO2 at 4.0 atmospheres over the liquid at 25 degrees Celsius, just room temperature. If the solubility at 1 atm is 0.030 molar, not very soluble. Well, if we increase the pressure above to much higher than 1 atmosphere, that should increase the solubility of the gas. So if we plug in our values and solve for X, we end up with 0.12 molar. It is significantly higher in solubility at a higher pressure. And that can force the CO2 to stay dissolved in the pop, and therefore it's going to be carbonated when we open it. Now, temperature is another thing that you should understand its effect on solids, liquids, and gases. Now, generally, the solubility of a solid in a liquid increases with increasing the temperature. It should make sense on a fundamental level. Why? As you increase the temperature, you're going to have particles moving at a faster rate. And as those particles vibrate and move around faster, that can free up some water molecules that used to be involved in the hydration as they vibrate away from the particle they're dissolving. And that frees them up to dissolve more. So in general, and you can see this in most of the situations here, in general, with solids, solubility increases when the temperature increases. Now, before we get into the next one, which is our gases dissolved, our nonpolar things dissolved in water, not our solids, we're going to look briefly at something that some of you may have noticed in the kitchen before. Why do bubbles form on the inside wall of a cooking pot when the water is heated on the stove, even though the temperature is well below the boiling point? So you dump your water in your pan to make spaghetti and turn on the stove, and as time goes by, it's going to take a while because it takes a lot of energy to boil water as we look at its heat of vaporization being very large. So it takes a lot of energy, so it's going to take a while for this to boil. But if we look inside the pan, over time, we're going to start to see on the sides of the pan all of these gas bubbles appearing. It's not actually boiling, but those gas bubbles are going to appear and get larger, and they're going to break away from the side and float to the surface. You're not actually boiling. What you're doing is you're affecting solubility of gases. Increasing the temperature of the water actually decreases the solubility of dissolved gases. And this is, like solids, usually true. This is always going to be true of gases. And those released gases deposit on the side of the container and build. So that's evidence that gases are different than solids in terms of solubility. And as a nonpolar substance, it would make sense why that's true. Those things aren't very attracted to water molecules. So at higher energies, you shouldn't be able to dissolve as much as those particles achieve the energy to break away from the water molecules and escape from the liquid. And remember, the basic idea here is then opposite with solids and gases. And you can see this with pops. We store them cold. Why? Well, because the solubility increases at lower temperature, and that's going to keep a little bit more of the CO2 dissolved in the pop and keep it from going flat. It also has consequences to fish because fish live in water and they breathe that dissolved oxygen. They actually filter that out of water, and that's what they use to breathe. So if the lake is warmer, there's going to be less dissolved oxygen in the lake. And a lake that gets too warm, the active hunting fish aren't going to survive. While your more sluggish scavenger fish, which don't have as high of a metabolism, are going to be able to successfully live in that lower dissolved oxygen atmosphere. So something like by a nuclear power plant, they have to closely regulate the temperature of the water that leaves the plant that's used in the cooling process before they dump it back in the river. Not because it's potentially radioactive, but because of thermal pollution. If it's too warm, there's not going to be as much dissolved oxygen, and that can actually kill the fish in the river. Now, the last thing we're going to get into today is concentration. Now, remember, concentration can be expressed qualitatively. You can refer to something as dilute or concentrated, or it can be expressed as a quantitative value, like mass percent, part per million, part per billion, and molarity. These are the four fundamental types of concentrations that we're going to look at calculating and using and understanding. So first, mass percent. Like all percentages, this is part over whole times 100. The reason is the part over whole gives us a ratio of 1, but it's going to be a fraction. And people don't like fractions and decimals. So if we multiply it by 100, we get a more normal number. So 60%, 60 out of 100, people are more comfortable with that than 0.6. So you take the mass of the solute and divide it by the total mass of the solution, multiply by 100, and you get your percent by mass. So what does a 4% NaCl solution actually mean then? Well, it means that we have 4 grams of NaCl dissolved in 100 grams of water, and therefore, I should say not 100 grams of water, 100 grams of solution. Technically, this would be 96 grams of water because masses are additive, and if we know the total solution is 100 and we know the solute was 4, that must mean our solvent, in this case water, was 96. So that's what a 4% solution means. Now, another way to express percent mass and percentages is to use the term parts per hundred, pph, because literally it's how many are in 100. So we can also have PPT, how many are in 1,000, ppm, how many are in a million, and how many are in a billion. But we don't usually use PPT all that much because parts per thousand is going to be close enough to parts per hundred that we're going to, even with lower concentrations, if it's not too low, we're still going to get more normal numbers when we're dealing with percentages. But when we deal with things with very, very, very low solubilities, you get such a small percentage, we're probably going to express it in scientific notation. And once again, people aren't comfortable with that. So that's where parts per million and parts per billion come in. When we have things with very low solubilities, these would be an appropriate way to measure concentration. It's the exact same equation, but instead of multiplying by 100, we multiply either by a million, which is 10 to the 6th, or we multiply by a billion, which is 10 to the 9th. And remember, be careful putting these in the calculator. 10 to the 6th is not 10 EE and then 6. That's 10 times 10 to the 6th. We want 1 times 10 to the 6th. So 1 EE6 is all you need to hit. Or just multiply it by a million, 1 with 6 zeros after it. But these are very, very similar to percentages. We're just multiplying by a different number, so we get more normal looking numbers at very, very, very low concentrations. Now, the last one we're going to look at, we've already talked about in first year chemistry and early in the year, and that's molarity. So we already discussed this in chapter 4. Molarity is the number of moles of solute divided by the number of liters of solution. So if we knew the amount in grams or moles, and we knew what the volume was of the solution, we could determine the molarity of that solution. And we use this quite often in everyday applications in chemistry. More so than typically we would use percentages. But percentages are great for the general public because they're much easier for them to understand. Now, since volume of liquids is temperature dependent, molarity will actually change with temperature. And if you recall from first year chemistry, the molality way of expressing concentration, which we're not going to use this year, so we don't need to worry about it, that was actually temperature independent, which is why we used it in freezing point, depression, and boiling point elevation type problems. Now, the last thing that you should be able to do with concentrations, besides calculate them that we're going to talk about today, is how to make solutions from solids and from concentrated solutions. So if we want to make a certain volume at a certain molarity, so I've got a lab and I know I need 175 milliliters of this specific substance at 0.02 molar concentration. How do I go about weighing out the appropriate amount and making that solution? Well, that's something that you should understand for the AP test and for my test. And it really involves using the molarity equation. And what we really have to do here is determine the moles of solute in this volume. So if we take the molarity times the volume in liters, that would give us the moles of solute. And then we can use a molar mass conversion to convert that moles of solute into grams. So it starts really with using this equation to determine the moles of solute, and then we just do a molar mass conversion to finish it and figure out what the mass is. Now, the other thing you need to understand, there is more than just this. You have to also understand how you would make this solution. And the fundamental idea is you're going to dissolve, or I should say, you're going to measure out that mass, and then you're going to dissolve it in a smaller quantity of water than the total volume that we're going to end up with. Because if we put the correct volume in there at the beginning and we dissolve a solid into it, our volume is going to go up a little bit and we no longer have the appropriate concentration. So what we have to do is dissolve it into a smaller quantity of water, and then we're going to dilute it with water to the final volume. So it's a two-step process, and it's important you remember those two steps. So once we've determined the mass, we dissolve it in a smaller quantity than we need for the overall solution, and then we're going to dilute it to that final volume. Now, the other thing you should understand, we also talked about this back in chapter 4, and that is making a solution from a solution itself. So you're performing a dilution. So whenever we're making a solution from an aqueous solution that's more concentrated, we're going to be using the dilution equation. So what we're fundamentally doing here is we're solving for V1 using the concentrated solutions molarity. That would be our M1. And we know the volume and the molarity that we needed to end up with. So we know the V2 and M2. All we really have as an unknown is our original volume. Now, once we know what that volume is through this equation, you have to remember the same two steps is fundamentally what we're going to do in this situation as in the last one. You're going to measure out that volume and you're going to mix it or dissolve it in a smaller quantity of water than is needed. So if we needed to make 175 milliliters, we're going to dissolve it or mix it in 100 milliliters, and then we're going to dilute it to that final volume so we actually get the concentration we desire. And that ends our notes today.